Good morning all of you. Today let us discuss on open channel flow. This is the last class on open channel flow. As we discuss about the specific energy, and today we will solve a few problems, as well as we will discuss about hydraulic jump and the best hydraulic cross sections what is required for designing a canal structures. So, as I told in previous classes that the mostly we are following it Senthil Simbala books and some part of Hanif Chaudhary books or the FM White. This is, as you know it, very simple chapters with lot of assumptions. We design this open channel flow, flow under a sluice gate, spillway, many civil engineering structures. So, we try to design based on this open channel flow. The basic concept what we use is we will talk about that the conservations of mass and energy equations. So, these two equations as we consider for the one dimensional flow, that is what we have simplified it, one dimensional incompressible okay, steady flow. So, that is the reason it is a very easy to solve it as compared to we have solved many complex problems, but when you simplified it, the flow is one dimensional, incompressible and the steady flow. So, that is the reasons we have tried to look at the basic idea to know it, the flow depth variations in a open channels, the velocity variations, how the velocity changes it, how much of energy losses, energy losses is happening it because of the flow, and mostly it is governed by the gravity forces and the frictional forces as I discussed earlier. So, we have just two force component, the gravity force and frictional force component. These two force components are there when you talk about a open channel flow. As we discuss about the specific energy and the critical depth, the same concept we will talk about, and more details I will today talk how we can use a specific energy which is a graphical representations of energy versus the flow depth of a channel's cross section, where the datum is considered is a channel bottoms, more or less the horizontal channel slopes. So, in that case we can use a specific energy concept, that is to understand how the flow variations will be there, and most important again I am to repeat it, that subcritical flow, as we discuss more details, subcritical flow, that means when you have a flow Froude number lesser than 1. So, in terms of the flow velocity, in terms of the speed of the surface wave, you can interpret it what is the conditions comes it when you have a subcritical flow. When you throw a stone to a rivers, if you have a subcritical flow, the wave will be propagates both upstream as well the downstreams. Then we have a very the critical flow, which will have a the flow Froude number is equal to 1. That is the conditions we have when you have a the critical flow. That means the flow Froude's number is equal to 1. Physically, if we try to understand it, the velocity of the flow is equal to the speed of the surface wave. That is what we did it. Then we have supercritical flow. where the flow Froude numbers is greater than 1. This is what is a recap what we discussed in the last 2 classes. Also, we are going to discuss about best hydraulic sections, as it comes a simple questions in GATE or engineering service exams. That part also will be talk about that. Let us come back to the hydraulic jumps. How does it forms it? If you look at that, if you have a more or less the horizontal surface, okay, more or less you have a horizontal surface and you have a sluice gate, okay, it is a gate operating it. Okay. The flow is coming from this side, it has a depth. Okay. After that, you can see that flow will be like a jet flow, it will happen like this. Okay. So, this is the gate which is we are operating, this is what a gate, the flow is coming from this side and is going out. So, we can see that the typically it will have a jet type of flow, the flow will be move like a jet type of flow. Okay. And you can blow it, very simple idea. If this y 1 is the depth, here is y 2 is depth. If I follow as a steady flow, so the mass conservation equations give me that very basic thing, that rho is the density multiplied with the q, that is mass inflow is equal to mass outflow, that is what is q. In this case, if this is the v 1 velocity and this is the v 2 velocity. So, I can write it rho v 1 y 1 and b is a perpendicular depth or the width is equal to rho v 2 y 2 and b. So, b be cancelled out, rho as a incompressible flow and the steady flow. So, we have a v 1 y 1 is equal to v 2 y 2. What do we mean by that? As the depth decreases, the velocity is going to increase it. Okay. That is what a very simple way we can understand it. If the depth of the flow is decreases, then the velocity increases. As the velocity increases, does it go to a supercritical levels or not? As I am operating a gate, okay, as going down and going down. So, there will be a conditions will come it that this gate will come at a critical flow. Okay, that is what the critical conditions will prevail it. Beyond that, it will go subcritical, supercritical level. You look it just to try to understand it, the gate I am lowering down. So, as I get I lowering down, my y 2 will be lesser and lesser, v 2 will be larger than the v 1. And if I estimate the flow Froude numbers, so I am reaching towards to supercritical flow, reaching towards to supercritical flow. But that means this will be the conditions, we will have a flow Froude number less than 1, these the conditions we will have a flow Froude number greater than 1. Okay. That depending upon the flow velocities. Okay. But mostly if you come to this, you can have this subcritical flow, you can have a supercritical flow. Okay. But if I will create it a simple, the same structures, okay, there will be a gate, there will be a gate, this is the channel bottom, there will be gate, it is a channel bottom is there, but here I create a humps, create a some sort of a hump, a bump type of things I have created. So, what will happen is that if I lower the gate, the flow will come it here then here it will commit, then there will be hydraulic jumps, then the flow depth will be maintained like this. Okay. The flow bed depth will be maintained like this. See, if I take a section here 1 1, 2 2 or 3 3. So, these regions I will have a flow which is less than 1, this is the regions flow greater than 1, less than 1. So, this is the supercritical flow to subcritical flow. When the flow passes through the supercritical to subcriticals with a very limited ranges, then there are a lot of turbulent structures created. Okay. That lot of mixings, the turbulent structures are necessary created. That is what we call hydraulic jump. That is what is hydraulic jump. There is a energy losses happens. There is a energy losses happening when the flow goes through the supercritical. Please remember, supercritical to subcritical. Supercritical is to subcritical regions. It is creates a jump. You can see that this is a jump behavior. This is the jump we call a hydraulic jump, and these the hydraulic jump create a lot of turbulence structures. The noise, if you go to just any spillway or dam structures, if you visit it, or today you have Google with you, you can just browse it and see that how the hydraulic jump formations happens just downstream of a dam projects. Okay. Especially during the monsoon periods, you can see the noise, the turbulence structures, all you can see today's. Okay, because you have lot of sources like Google and YouTube and other sources. You can just browse it and see how the hydraulic jump formations are happening, which is quite beautiful. So, okay, sometimes because of hydraulic jumps also there is a rainbow formations happens, it which that type of conditions you can see it. So, it is a quite beautiful that way, but also it helps engineering also. We look at the hydraulic jump because that is a zone we can have a lot of mixings of air mixings or chemical mixings. So, engineering also we need to know design it such a way that there should be a hydraulic jump which will be create a good mixings of any chemicals or air bubbles. We try to do it the mixing process with just creating a hydraulic jump. Okay. And bigger hydraulic jumps you can see it, and smaller hydraulic jump also happens it in real life. So, you can see when the flow changes from supercritical to subcritical regions. That is the reasons we will have a hydraulic jump, and also we will have a energy losses. We will have energy losses. So, if you look at how do we really analyze a hydraulic jumps, that means if I know the upstream conditions, okay, very simple way, just to look at the hydraulic jump part, I can just simple way write it. It is a jump like this. Okay, it is a jump part. Here again I am writing a cross section 1 1 1. So, just to you to coming back to the book levels, which is given in the pre-upstreams, we will have the 1 1 and downstreams will be 2 2. So, that means at the 1 1 I have a y 1 flow depth, I have a flow Froude numbers, upstream flow Froude numbers, I have a velocity. Similar way I have a y 2, I have a v 2, I have a flow Froude numbers at the second level. That is what you can look at. Okay. So, if you look at these problems, okay, that is what is a the same concept what I have sketched it, that is what is figure is here. Now, if you look at the problems what we are talking about, we can always look at that how the things are happening at this point. Okay. So, that what we can make it, how this point is happening. This point is very simple. That means, I can use a control volume, just I have to sketch it as I taught you very detailed about control volumes. So, just do a control volume. how I will analyze a hydraulic jump. So, let me resketch the problems. So, what I have the problems, it is a very simple problems I have, that I have a upstream flow, it is a coming it, there is a hydraulic jumps, then flow is coming here, it is a steady nature now, this is the downstream, the flow is coming here and going out here. So, let me you have a v 1 velocity, y 1 is a flow depth, you can compute the flow Froude numbers, you can compute the specific energy. Same way you can velocity, flow depth, flow Froude numbers at upstream, and you can also compute specific energy, which is a very simple way, E equal to y plus v square by 2 g. So, we can compute the specific energy at upstream as a downstream. Because of the hydraulic jump, as I emphasized that the energy losses happens. So, if I am to draw energy lines or energy gradient line, so how it will come it? Okay? This is y 1 depth, this will be v 1 square by 2 g, that means this is the locations up to this, and I have a this point. So, energy line will come like this, this is the energy gradient line, there will be energy losses, that what will be reflected in the energy gradient line. And if I put it, the energy losses due to the hydraulic jump is H L. Okay. Energy losses due to the hydraulic jump is H L. So, very easily I can write it, energy conservation E 1 is equal to E 2 plus H L. The very simple things. Okay. So, it is very simple things to get it the energy losses. Okay. If I know the specific energy at upstream, specific energy at the downstream, just subtracting that I will get the energy losses. How to get the V 2 and Y 2? Because upstream conditions we know it, V 1, Y 1, flow Froude numbers, the specific energy, but we do not know V 2, Y 2. If you know the V 2, Y 2, we can compute the flow Froude numbers as is a subcritical flow, that should be less than 1. And then you can V 2, Y 2 know it, we can estimate the specific energy at the downstream levels. Okay. So, then you can compute the energy losses. What way we can solve the problems with us? It is a very simple thing. As I have considered this is the control volume, I will just apply the two equations with me, mass conservation equations and momentum equations. Anyway, we are using the energy equations to get this, the loss due to the hydraulic jump formation. So, I have two equations, I have two unknown. So, I can estimate it, that is what very basic things. Okay. More detailed derivations anyway I will show to you, but basic thing is that we use the specific energy to know it, how much of energy losses is there, and once I know this energy loss components, okay, then I can design the hydraulic jump. So, how to get this downstream, the velocity and the flow depth V 2 and Y 2, that is what we will be do it with help of mass conservation equations and the linear momentum equations, as we used to do it for other conditions for that. Let us come back to the again is a repeating it, that the specific energy curve and specific energy curve and hydraulic jump H. How does it comes it? Okay. Hydraulic jump. Let us try to understand that. Okay. Specific energy curve, as I yesterday in the last class we just discussed it, that it is the graphical represents of specific energy versus flow depth. And when you draw a line, the specific energy is equal to the 1, which is 1:1 line, and since we have derived it, the specific energy curve will come like this. Okay. So, please have a practice to draw the specific energy curve for a particular discharge, let be the Q1, but another discharge, if you draw it, it will come at Q2. Q2 is greater than Q1. This is simple things, you just interpreted the relationship between the specific energy and discharge and the flow depth, you will get these curve natures of U1, U2 are the constant discharge. I can draw a functional relationship between for a constant discharge. Mostly this canal and others we design for a constant discharge. Okay. So, for that constant discharge, we can have the specific energy versus y, the relationship, that is what is we can draw it. Okay. And as this Q2 is greater than Q1, your again if I draw a Q3, so never interact each other. Okay. The Q3 will be larger than Q2 and Q1. So, more detail you can go it, look at the books of Hanik Choudhury and all, but as undergraduate levels, let us have these things. Now, if you try to make it very interestingly, that let we have the upstream flow. Okay, for constant discharge Q1, I have a upstream flow, okay, which is ES1. So, that means upstream flow can be subcritical, can be supercritical. Okay. Can be subcritical, can be supercritical. Okay. So, upstream flow can have a two alternative depth, okay, subcritical or the supercritical, but as we said it very clearly, the hydraulic jumps occurs from the flow from supercritical to subcritical. Okay. So, higher velocity flow to the lower velocity flow, that is you can. So, that way if you look at that, so let me I have upstream specific energy ES1 and this is what is crossing it. So, being a conditions to have a hydraulic jump formations, the point is lies here, point is lies here. So, that what I can look at very clearly, this point is here. Okay. But as we know it, if there is a hydraulic jump, there is a certain energy losses, that means the next point will come it here, okay, which will be HL, the energy losses just downstream of this, because energy losses happening, it will come down in a figure will come towards this part. So, we will have a point, this will be the subcritical flow. So, that means when you have the hydraulic jumps, the flow changes as you know it. This is the regions which will have a flow Froude number greater than 1, the flow number less than 1. So, it jumps from subcritical to supercritical. So, that means this is the directions flow it, and there is a energy losses of HL. So, always you can sketch the specific energy diagram, try to understand it, how the flow moves it when there is a hydraulic jumps. Drawing the specific energy curve, you can find out how these things will come it. That is what I said it when we constructed in our civilization, the construction of canals and all the things are 4000 years old. So, we used to use a simple graphical technique to understand it, how much of energy losses is happening it, and there are so many hydraulic experiments conducted throughout the world to understand the hydraulic jumps. Okay. Not only in India, this University of Roorkee, but or IIT Roorkee presently we known, but the hydraulic jam formations and all things, a study has been done almost 100 years back. So, let me I come back to very basic things as because most of the times we generally have a rectangular canal drainage lines and all. We generally prefer to have a rectangles because it is easy to construction. The construction is very easy, okay, to construct a rectangular channels. Okay, if that means it is very simple things. Okay, B, and if you have a flow depth, let be H. We just try to locate that what is the as you know it, the specific energy is minimum at the critical depth. So, we need to compute the relationship between the specific energy, the minimum specific energy. So, basically we are looking it again, I am drawing the specific energy curve and drawing. So, this is what E minimum. We are looking at what is this conditions, okay, for E minimum versus the YC, okay, critical depth. Okay, this is the YC. What is the relationship with a E minimum for a rectangular channels? It's very easy part. Okay, if you look at that, you just compute the E minimum. If you look it, that is what will be in terms of YC and VC, and just you substitute the relationship between this charge and YC, which we get it from simple from the Froude numbers is equal to 1, you will get this relationship. It is a very simple things. Okay, Froude number equal to 1, you will get this relationship. If I substitute this, the finally what we are getting it, that E minimum, that means this coordinate will be 1.5 times of YC, which is quite easy, okay, for rectangular channels. Is many of the times we just use the rectangular channels from drainage systems and all. As I am discussing about the hydraulic jumps, I am not going detail about hydraulic jumps as I just discussed that, but I will just highlight it. When you have the hydraulic jump, what are the assumptions we put it, which is get a some sort of a theoretical value of hydraulic jumps. Okay. This is the section 1 this is the sections 2. Okay. So, you have again I am putting y1, v1, specific energy, y2, v2, specific energy, Froude numbers, Froude number 2. So, we need to do a control volumes to solve this problem. So, we need to have a control volume. So, I consider a control volume like this. This is my control volume. So, I need to know it what are the assumptions as we did it. First is the pressure distribution here is as it was a hydrostatic conditions. Okay. The dynamic pressure is close to the hydrostatic pressure distributions. Okay. So, I have the pressure distributions, which is assumption is that as close to the hydrostatic pressure distribution. No doubt there will be velocity distributions as we discuss it, but in this case the V1 and V2, in this case we consider the beta 1 and beta 2 momentum flux correction factors close to the 1. Okay. Somewhat these approximations are correct for a turbulent flow where the B1, B2 will be close to the 1. Pressures varies hydrostatically, that is what I sketch it, and the wall shear stress and associated losses. Okay. the wall shear stress, okay, at this wall the is equal to the 0. It is quite simplified it. Okay. Basically, we are looking at that the force because of wall stress will be the much lesser than the pressures generated by the hydrostatic pressure fields. Okay. Hydrostatic pressure field, it is not a hydrostatic, okay. Flow is there, but the pressure disturbance is close to a flow at the rest conditions. Okay. So, as you have the control volume, already you know the beta 1, beta 2, already you sketch the control volume, you know the influx is going outflux, you know the mass influx going mass outflux, momentum flux and going out that you know it, the linear momentum equation tells about sum of the force is equal to the net momentum outflux. That is the basic equations what we need to use it. That is what here. So, is a mass conservation equation. Okay. Please note that there is no rho and b, but it is okay. The flow is incompressible, so the density is constant. So, we have a relationship as I derive it is the V 1 is equal to y 2 by y 1 V 2, or reverse you can always do it. What you need to have, sum of the force is equal to, that is what is the momentum equations, is the net outflux of momentum flux beta times of mu and b out minus in. Okay. The negative sign things you just look it. So, I compute the hydrostatic pressure distributions, and after substituting these you just rearrange the terms, more detailed derivations always you can look it Sinzel-Simbala book. Just rearranging the pressure average, what is the pressure component is coming it, okay, as you know it, the pressures will be the average pressures P 1 average pressures will be half of rho g y 1, because this is the rho g y 1 by 2, half of the rho g 1. This is the pressure, average pressures acting at the section 1 1. Similar way sections 2 2, and if you do a systematic derivations, finally I get a relationship with a y 2 and y 1 this. Okay. Just for your sake I can just write it, y 2 is a flow depth at downstreams is a functions of 0.5 minus 1 plus square root of 1 plus 8 flow Froude number of upstreams, okay, is this. So, this the relationship gives us the, because in upstreams I know a flow depth, I know these flow Froude numbers, substituting these values because it satisfy the mass conservation equations and the linear momentum equations, I can get it this relationship. Okay. I can get it this relationship. The same way I have to look at the energy dissipation ratio is nothing else the HL by the upstreams specific energy. The same way I can get the HL as I explained earlier, I can get the HL functions, head losses, and then I can just substitute it. So, these are very simple thing, just arithmetic way you can solve these problems. Now, let me, I am not going more details because if I go for higher classes you can do it, the what type of hydraulic jumps formations happens it, and we consider the different type of hydraulic jumps, but I just want to say that when you have the flow Froude numbers, okay, is a range of the upstream flow Froude numbers is range between 4.5 to the 9. Okay. So, flow Froude numbers if you have the ranging upstream things, then there will be a huge energy dissipations. Okay, that is the supercritical regions, and if you have a flow Froude numbers 4.25 to this, the energy dissipations will be the about 50 to 70%. the flow will be the steady jump formations there. The jumps will be the remaining at the steady conditions. If you go above the 9, then you will have a strong jump formations. Energy losses will go in order of 70 to 85%. Okay, that's the basic calculations, the basic idea, and we go for classifying the different type of hydraulic jumps, but I am not going detail for this undergraduate course level. Now, let me solve a very simple problems. Okay, just substituting these values, we can solve these problems, and if you understand how the hydraulic jumps happens it and how the upstream and downstream links flow characteristics are interrelated, you can solve this problem, and it is a very simple problem. The water discharging into a 15-meter wide rectangular horizontal channels, okay, with a sluice gate have undergone a hydraulic jump. The flow depth velocity before the jump is 1 meters and the 10 meter per second is the velocity. So, what is given it? Y1 is given is 1 meter, okay. The velocity is given is 10 meter per second. I think B is given here 15 meter, but B is not necessary to compute this. Compute the flow depth, flow Froude numbers after the jump, that means Y2 and V2. Head of energy losses or energy dissipation ratio. So, as we discuss it, you can get this energy losses HL, you can get energy losses by specific energy, upstream specific energy. The assumptions are the flow is steady, that is okay, and quasi steady, channel is sufficiently wide, there is and effects can be neglected. Density of water as considered 1000 kg per meter cube. Now, first we have to check it whether the flow is the supercriticals or not. What is the flow Froude numbers at the upstream levels? So, that is what very simple, as the flow Froude numbers is equal to, again I am highlighting it, velocity of flow by the speed of surface wave. The speed of the surface wave is C naught is square root of G y. So, y is here y 1. So, we just substitute it, it is greater than 1. So, flow Froude number is greater than 1. So, it is supercritical flow, that no problem, as it expected. So, then it will have the hydraulic jump formations. We use that linear momentum equations relationship to compute the y2, which is coming around 4 meters. Okay. With a continuity equations, we can get it what will be velocity in the V2, and we can again compute the flow Froude numbers at the downstreams at the sections 2, okay, as it is less than 1 is subcritical. So, all these conditions are satisfying it, their flow is going from subcritical to supercriticals. The flow Froude numbers, you need not to remember it, it is a ratio between the velocity of flow by the speed of surface water wave. The speed of surface water wave having a relationship C naught G into y, y is the flow depth. For y1 depth, the speed will be G into y1, for y2 depth, that value C2 will be G y2, that is all. So, these two ratios define the flow Froude numbers. So, if you do not remember the flow Froude numbers, at least you remember this part. Okay. That is the speed of surface waves, okay, speed of surface wave. This is same way estimate the head losses, the dissipation ratio, it is coming at 6.01 and all these numerical values if you look it. that how much of energy losses are happening it and how much of the dissipations, which is 0.28, means about 28% of energy loss is happening it. Okay. 28.6% of energy losses are happening it because of the formations of hydraulic jam. Second problems is very interesting problems which we have taken from Hanif Chaudhary book. A bridge is planned for 50-meter wide rectangular channels and carrying a flow of 200 meter cube per second. Flow depth is 4 meters. We reduce the length of the bridge. What is the minimum channel width so that the upstream water level is not influenced by the discharge? So, indirectly it is talking it that when you are reducing the depth, okay, that is what again I can sketch it, you can understand it this way, okay, this same specific energy. So, you can really draw the specific energy for Q, small q, discharge per unit width. We can compute this part. Okay. So, that way I can have this values of Q1 constant, Q2 constant and Q3 constants. Okay, this is specific energy. It is saying that let me I have a point is here. Okay. As I am increasing the B, so I am increasing the Q3. So, I am coming to closer to a level where I am reaching to a discharge which will have a E minimum. Okay. That means, I am coming to a level where I have a unit discharge corresponding to critical depth. So, that is what is reaching it. As just track on, as I am increasing the B width, reducing the B width, reducing the B width. So, my discharge curves is going down and down, okay, and it will be reached to a point where that discharge meeting with a E minimum. After that, flow does not occur it. That means, for that discharge, it is a critical depth. For that discharge, it is a critical depth. So, when you are reducing the width of the bridges, okay, you will come up to the critical depth. So, if you go beyond the critical depth, then there will be choke conditions will happen. So, which we can go try to understand more details in higher classes. So, choke conditions will happen. To avoid that, we try to maintain that the flow should go at most to the critical flow levels. So, that is because it is a rectangular channels, you know the specific energy what is coming it. For this specific energy already we have relationship with a critical depth which is so we know the critical depth, and for that corresponding discharge for the critical depth also we will get it. The width of the reverse for the BC is coming to 15 meters. Okay. Okay. That is the width. So, initially width of 50 meters, but we can come up to the close to the 14.4 meters. Okay. That is the depth we count with, that unless there will be the effect on the upstream water levels. Because of that, bridge also can have a upstream effect in terms of more submergence will happen it. To try to avoid that, we try to design as a critical depth concept. Mostly I try to say that you can have the specific energy curve to analyze it. Another things which we generally talk about in GATE or engineering service exam, but today's we have a much more sophisticated design softwares are developed it. Okay. It is not that easy simple way to design when you design a urban drainage systems or you design a big channel networks which is very complex. Okay. It is not like simple way to design a one cross sections. Okay. So, that is the reason there are lot of design softwares are there to solve the problems. Okay. But as curriculum concerns, we call a best hydraulic cross section. What is the best hydraulic cross section? Okay. it is not best, he is looking for best anything related to flow, it is related to the economy. That means, if you look at that, if I want to construct a channels, okay, which is I said it channel from a point 1 to point 2, okay, have a water flow or any liquid flow from 1 and 2, the points are fixed to carry this water or the liquid from 1 to u. So, the slope is more or less fixed, slope is more or less fixed, we cannot change it, the slope more or less fixed unless we can put the drops and all, but we can have the a point 1 to point 2, we have a constant slope. Okay. So, for the q amount of discharge has to go it. Okay. So, this q as a design parameters, what we are looking at? Design parameter. First is safe, right, we can have with us. Okay. Slope is more or less fixed because endpoints are fixed for us. So, one is a safe, you can have a rectangulars, we have a trapezoidals, you can have semicircles or circular pipes. So, the shapes are can be different type of shapes, that is what option with us. What is the relationship with the perimeter and the depth, because constant discharge is known for the design discharge. This is what design discharge. So, q is a fixed for us, only options with us as a designers. Okay, as I said it, nowadays we have a lot of softwares are available to do that, but basic concept follows same, that if you have you have an option for the different shape, maybe rectangulars, maybe trapezoidals, maybe the semicircles or the circular pipes. Okay, we can have that. Now is coming it that others is that I can have a different perimeters and the flow depth, that can have this. If you look at that, basically we talk about the construction cost, okay, which is directly proportional to the perimeter. That is what it happens, the cost directly proportional to the perimeter. So, that is the reasons we have to, we look at the perimeter is P, we try to minimize the perimeter P. We try to minimize the perimeter P, because the initial cost will reduce it. The minimum P, the cost will be the less, because length is more or less the same. So, if you look at that minimum the size of systems is a minimum cost of construction. Smaller the resistance zones, average large average velocity and flow rate. Okay. The resistance we have to reduce it, that means you need to have a concrete channels. Okay. If you reduce the resistance, your velocity will increase it, the flow carrying capacity will increase it. That is the reasons we cleaning the drainage system so oftenly, otherwise it raises. Maximum hydraulic radius, which is maximum average flow velocity. Okay. So, basically best hydraulic sections, which is that maximum hydraulic radius or minimum wattage parameters for these specific cross sections. Okay. I just want to repeat it that maximum hydraulic radius will give you a maximum velocity. Okay. I am not going to that equations, but I just want to put it the meaning equations, because it's the velocity is a proportional to the hydraulic radius. Okay. So, that is the reasons maximum the velocities is we have a maximum average velocity. So, we try to look at the aspect ratios, flow depth by the channel depth y by b, and we are just looking it for a rectangular cross sections, what will be the relationship between b and y, so that the perimeter should be minimum. Okay. That is the simple things. Okay. So, we try to look it first, a flow area is equal to y into b, y and b. Perimeters, you can see that b plus 2 y, and we can write in terms of perimeters, b we can remove it, and to make these functions minimum. So, dp by dy is equal to 0. That conditions, when you put it, you will get it y equal to b by 3. That is the best conditions in terms of constructions, because that is the conditions your perimeter is minimum. Okay. So, y will be the b by 2. That means, the y will be the half of the channel width. That is the best cross sections for rectangular cross sections. What we can, same way we can go for trapezoidal cross sections, where we can talk about, define the area, perimeters, then we can again do this differentiation with respect to y, then we can get it y is a function of theta, theta is here, functions of b and the theta. That is what we look at, and we also look at that hydraulic radius. You can compute the hydraulic radius, which is area by the perimeters. You can just substitute it. Finally, you get it, hydraulic radius will be y by 2, and dp by theta is a best. The minimum conditions will be theta should be 60 degree, and the relationship between y is 3 root 2 by b. Okay. That is the best conditions. Same way, I am not going details. You can go for a circular channels. You can look this how to do this. These are simple things with considering a 2 theta, and geometrically compute the area, compute the perimeters, then you make it the dq by d theta is equal to 0. Okay. And you try to solve it, and dp by d theta, and you try to get a relationship between maximum velocity conditions, and that is what we do in hit and trial methods. More details I am not going it, all details are there in Sindel-Simbala book. You can go it. Similar way, you can talk about a triangular channels. In most of the times a low flow velocity, we need a triangular channels like urban drainage. So, we can find out the relationship between hydraulic radius and the flow depth, and if you are making it economical channels dp by dm. Okay. M is representing here. So, we will get a relationship, the same conditions, okay, getting the area, getting the perimeters, getting the hydraulic radius, and you try to look at what is the conditions come it for dp that, and theta is 45 degrees, the best conditions here, okay, and m equal to the 1 conditions, that is the best hydraulic cross section. Now, I will just look at one example from Sindel-Simbala book. Water is transport with a discharge is given, open channels, line, the slope is there, determining the best cross section if the shape of the channel is rectangulars and trapezoidals. Okay. If you look at this condition, okay, you can highlight the assumptions, okay, flow is steady, uniforms, and all these conditions. Okay. And you can just substitute basic case of rectangular cases and use the Manning's equations to get this velocity and b and y components, okay, as you know it the flow velocities. Okay. Similar way we can do for trapezoidal cross sections with help of Manning's equations. Okay. I have not gone very detailed about Manning's equations, but you can have Manning's equation, and finally, you get it what will be the b value for best cross section hydraulic cross section, which is necessary, as it will be the minimum construction cost. With this, let me complete it to for this open channel flow. You have to remember very simple things. One is the speed of surface water wave, which is a function with G and the flow depth. That is what you should remember it from this class, and the flow Froude numbers is V by C naught. Okay, that is what is basic concept we discuss a lot. This is the concept also energy, specific energy concept what we have introduced it, and the critical depth also we have introduced how we can, but in order to remember much except this one. With this let me I thank my students group who is really they help for me to develop this very interesting illustrative and with a lot of examples of demonstrating this how to solve simple problems or complex problems for this. Thank you a lot.